Number 3, define a subgroup of a group G. So there are many equivalent ways to define a subgroup. My favorite way is like this. A subset H of G is a subgroup if, when you give it the same operation, well, I guess I should try to match the symbol. When you give it the same operation, the star, that subset is also a group. So that's not guaranteed, right? You know, like if you have a group, you know, like the group of integers, for example, and you pick the subset 1, 3, and 10, well, that's not a subgroup, right? Because, well, it's a lot of reasons, right? First of all, 1 plus 3 is 4, so it's not closed. So if H meets all the conditions to be a group by itself, then that is what we call a subgroup. There's other equivalent ways to define it, right? You could define it like this. You could say H star, I'm just going to say a star, is closed. It contains the identity. So whatever the identity element was of G, it contains that. And it's also H contains inverses. So as in anything that's inside of H, its inverse is also inside of H, right? So that's another equivalent way to define it. Now I want to clarify, you cannot leave that out. Some people said this, which is not correct, right? Let me give you the example. Z, we know, is a group, right? Starts with 0, 1, 2, 3, 4, and then it's also got the negative numbers, etc., right? That's a group because it's got an identity, it's got inverses, you can add everything together, it's another integer, and so on. How about, check out this subset of just the natural numbers. Is that a subgroup? Well, according to this definition, it is, right? It's closed. The sum of any two natural numbers is a natural number. And it also contains the identity element of Z. So according to this definition, it is a subgroup. But that's why this definition is wrong, because N is not a subgroup, because it's not a group, because it doesn't have inverses, right? The inverse of 2 is -2, and it's not in there. So this definition is insufficient to define a subgroup. You must also say H contains inverses. And that whole kerfuffle is why I strongly prefer to just define it that way. You just say it's a, you know, it's a subgroup if it's just a group, period. And you don't have to worry about any of that stuff. Okay, part 2. Let H and K be subgroups. Show that H intersect K is also a subgroup. Okay, well, we just got to show these 3 things. H star is closed, or sorry, H intersect K is closed. It contains the identity and it contains inverses. So here we go. Start with closure. Let's pick 2 elements in the set, right? And then we got to show that when you multiply them together, you're still in the set. Well, what does it mean to be in H intersect K? Well, it means that you're in H and you're in K. So we can say, so X and H, or they're both in H actually. X, Y in H, and X, Y in K. Now we know that H and K are subgroups, right? So H and K are groups by themselves, which means they're closed under the operation. So if you multiply X and Y together, well, that's got to still be in H because they were both in H already. And if you multiply X and Y together, well, that's got to be in K because they were both in K already. And check it out, X star Y is in H and it's also in K. Well, that's exactly what it means to be in the intersection of H and K. So there you go. So any 2 elements of the intersection, their product is also in the intersection, so it's closed under the operation. Parts of this proof are very similar. we just say for the identity, for example, H and K are subgroups. So that means that the identity is in both of them. And merely another way to phrase the identity is in both of them is like this. The identity is in the intersection. So there you go. So the intersection is closed and it also contains the identity. But as we discussed, that is not sufficient. We need to talk about inverses. So we'll just pick some element of the intersection. And we got to show that its inverse is also in the intersection, right? Well, the key to that is pretty much the same as it was for closure, right? You say, we know, well, I'll say X is in H and it's also in K, since that's what it means to be in the intersection. And then since those are subgroups, the inverse of X is in both of those, right? So this whole thing depends on H and K being subgroups and having all of these properties already. And so since X prime is in both of those, well, then that's exactly what it means for X prime to be in the intersection. So there you go. So separately, we have shown that it's closed, it's got the identity, and it also has everyone's inverse. And that is enough to be a subgroup, right? That is what it means to be a subgroup, is that it has all of those things to be a group. Now, a couple things I wanted to mention. Notice that when we're talking about the groups, right, part of the, where'd that go? Oh, I guess I deleted it. Part of the definition was that the operation has to be associative, right? So why are we not talking about associativity when it comes to subgroups? Well, the answer to that is that associativity says for all A, B, C in G, it's the case that blah, 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 whatever it says, right? Well, if H is a subset of G, that's automatically satisfied, right? It says this is true for all elements of G, including the ones in H. So it's definitely true. We can just say it's definitely true then that it's true for all A, B, and C in H because, well, what's H? Well, it's just a subset of G. So automatically associativity is, inherited from just being a subset of G. So you don't have to worry about that. You do have to worry about the other things though, because those are not simply inherited. And then one last thing I wanted to say, if H is a subset of G, of course we write that like that. But if H is a subgroup of G, we write it like this. We write it with a less than sign. Well, see, I didn't really do that very clear, did I? A less than or equal to sign. Meaning it's a subgroup, right? So it's not merely a subset. It's got its own group structure on it. I saw some people using this symbol, like a full triangle. Now that means a normal subgroup. So I don't think you've gotten to this yet, but there's a special category of subgroups called normal subgroups, which are very important and special. And so we use a special symbol to mean that H is one of those special subgroups. If you just mean it's a regular subgroup, then you must not use that symbol. You must use this symbol, right? Those two symbols mean, the full triangle means something very specific. It means that it's a normal subgroup. So if you're just talking about a regular subgroup, don't use that. Okay, that's question 3.